Hey math kids, we're going to keep going with mathematical induction. Here's our P of n, and so we're going to prove, we're going to write out some of these terms to show P of n a little bit better. So P of n, if we plug in a 1 right here, it's going to be 3 minus 1, so it's going to be 1 over 2, and that's going to be 3 plus 2, so that's 5. So it's going to be 1/10 for that first one. And then we add that to the next one. If we plug in a 2, that's 6 minus 1, which gives us a 5. If we plug in a 2, that's 6 plus 2, so that's 8. 5 times 8 is 40. And let's do 2 more, I guess. So if we plug in a 3, 9 minus 1 is 8. If we plug in a 3, 9 plus 2, it's going to give us 11. And so that gives us 88. And that's probably good. And then we're going to start getting 1 over 3n minus 1 times 3n plus 2. And then we'll get 1, or this is equal to n over 6n plus 4. Okay, so that's the claim we're making for Pn. And if we plug in a 1 for n, when we test P1, you see on the left side it's 1/10. On the right side, we get 1 over 6 times 1 plus 4. 6 times 1 is 6, plus 4 is 10, so that is also 1/10. And so P, the first case, is true. So now we can say that PK is true, and specifically PK is going to be 1/10, 1/40, 1/88 plus dot 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 plus 1 over 3n minus 1, 3n plus 2 is equal to n over, I should be doing k's on these, I'm sorry. Okay, there's PK, we know that's true. We're going to look at PK plus 1. And PK plus 1, 1/10, 1/40, 1/88. Plus, now I'm going to plug in k plus 1s for this. So 1 over 3k plus 1 minus 1, and 3k plus 1 plus 2. And then that's equal to, now I'm going to plug in k plus 1s for this. Plus 4. Alright, sorry if that's hard to read. Now we're going to take the blue and subtract the pink from it. And I know that feels kind of backwards, but imagine the blues on top. These will cancel, these will all cancel. This cancels this. And so we're just left with this one that's on top right here. Or remember, the blue was up here. So it's going to be 1 over, let's see, if we distribute that, that's 3k plus 3, and then minus 1, so that's 3k plus 2. So we get 3k plus 2. If we distribute this, we get 3k plus 3 plus 2, and so that's 3k plus 5. Alright, so we took care of that one. And then remember, the blue is really on top, so it's blue minus pink. So we're equal to k plus 1 over, distribute the 6. So it's going to be 6k plus 6 plus 4, which means that's just a 10. Okay, then we're subtracting this. All right. Now what it comes down to is we just need to prove that the left and the right sides are congruent to each other, or equal to each other. And so I think the first thing I want to do, I want to try to factor out some stuff on the bottom here and try to combine this fraction into one fraction. So this 6 and 10, I can take out a 2. So I get 3k plus 5, and that's good because there's a 3k plus 5 right there. That's still over k plus 1. And if I take out a 3 here, I'm left with, not a 3, I can take out a 2. Take out a 2 here, I get 3k plus 2. And that's the other one right there. Okay, so this looks like it's starting to work out. Just remember that that's equal to the yellow part. Now, what I'm going to do is get common denominators. So I'm going to do 3k plus 5, 3k plus 5, and then 3k plus 2, 3k plus 2. All right, so the new denominator is 2, 3k plus 5, 3k plus 2. And we get k plus 1 times 3k plus 2 minus k times 3k plus 5. All right. Now, what we're going to do is just distribute on top. So if we do that, we're going to get 3k squared plus 2k plus 3k plus 2. And if I distribute a negative k to this, I'm going to get negative 3k squared minus 5k. All of that is over this. All right. So this thing cancels this thing. 2k plus 3k is 5k, and that's negative 5k. So all those cancel. So we can simplify that to 2 over 2 times 3k plus 5 times 3k plus 2. These 2's will cancel and leave a 1 on top. And if we look at this, it's the same thing as we have here. And so we proved that everything is true. Okay. Still have a few more. Okay. So we have a sequence defined by u1 is equal to 1, and u of n plus 1 is equal to 2un plus 1. And once again, this is for positive integers. And then we need to prove that u sub n is equal to 2n minus 1 for all positive integers. Okay, so our Pn is that u1 is 1, un plus 1 is 2un plus 1 for all n contained on positive integers. And if that's true, then this needs to be true. Okay. So we need to test the first case. So P1 is just if n equals 1. And so if we plug in a 1 to this thing, so u1 is equal to 2 to the 1 minus 1, and that's 2 minus 1 equals 1. So the first term needs to be 1, which was in the given, or right here, and so we've proven the first case. Next, we assume P of k is true, and so uk is equal to 2 to the k minus 1. We know that that is true. Now we want to prove pk plus 1 to be true. And so we say uk plus 1 is equal to 2 uk plus 1. And we're going to go back to this method where we kind of manipulate pk. Oh, actually, we don't need to manipulate it on this one. But we're just going to take this and replace uk down here. So 2 to the k minus 1 plus 1. And we're going to distribute this 2. So we're going to remember that there's a 1 right there. So it's 2 to the k plus 1 minus 2 plus 1. We can combine these. 2 to the k plus 1 minus 1. Okay. And since we ended up with our other formula, we know that this is true because we started with something in this form and then we ended with something in this form. Okay, and that's all we have to do on that one.